who's giving a talk on optimal decision trees and how we can improve them. This is Dr. Michael Baer, who is a PhD from Stanford in electrical engineering, graduated in 2003, and he's now working at Electronics for Imaging up in Foster City, where he's recently started in the color group. And so without further ado, Michael?
Okay.
It's on.
It's on?
Yeah.
Ah, there we go. That was a little louder than I expected. Okay, so I'll have to speak up to make sure that I don't deafen you all. Anyway, as David said, I'm here to talk about decision trees. So specifically, I'm here to talk about fast, hard-coded decision trees. And what I mean by hard-coded decision trees is the narrowing of intervals to a desired number of intervals, such as illustrated here, where I have 1, 2, 3 intervals, and I have this code which will narrow the intervals to the ones that I want. When this code is compiled, it will produce assembly code that will look somewhat like this, that will compare an item, that will go on if an item is greater than or equal to it, and branch otherwise. And it'll continue to do that until it gets the desired interval, at which point it does whatever it needs to do. So first I should ask, why do we care about this problem? Well, we care about this problem because it is a problem that occurs in a number of situations. The most obvious is explicitly when you have ifs and elses, or implicitly when you have a case statement. When you have a case statement, it has to somehow decide which part of the case statement it gets to. It has to make the decision, and one way of doing that is a decision trees. Of course, you could also use a jump table, but in some cases, decision trees are better to use. And in some cases, you don't really, in ifs and elses, you don't have a choice. It's especially nice if you know the probabilities of the outcomes that you want to have. That way, the less likely outcomes can take a little more time, and the more likely outcomes can take a little less time. And what you want to minimize is your expected amount of time that you're going to take. And for example, if you know that your distribution output is a bell curve, for example, if you have a number of grades that you want to calculate, this is a good thing to do. And one of the reasons that it's good to do in the case of grades is because in grades you have to, in terms of academic grades, you have to figure out what the score the person got was and out of how many that is. Well, that's a division. Some processors don't have a division function or instruction, and in others, division is just very slow. If division is slow, or if you have to emulate division, it might be worthwhile to have a quotient search, and that's the way a lot of computers do emulate division, is they try to come up with a series of ifs and elses such that it can figure out what the quotient is. And if you know the probability of the outcome, the probability of your quotient, then you can tailor that to that particular distribution. Finally, a particular application that I'm especially interested in is that of fast data decompression. If you want to have fast compression and decompression, one way of doing that is Huffman coding. And in Huffman coding, when you try to decompress a Huffman code, if it's compressed in the quickest manner possible, what you'll want to do is to figure out first how long the current code word is based on the bits that appear ahead of you. And one way of doing that is to use a lookup table or a jump table, but in some instances it's more efficient to use a decision tree. So I want to now ask you if you can think of any other examples that you've encountered in your day-to-day work here. Well, maybe I could.
Classifiers.
A classifier. Yeah, if it's a classifier in terms, if it's a numerical classifier, then that's a good example. Any other? Well, I've probably given you enough over here, so let's get on and state the obvious, which is that if you do things faster on computers, you get happier users from faster performance, and sometimes you save money. If you have a server farm and you have a loop that's running over and over again, if you tighten that loop, if that loop involves a decision tree, then you have to spend much less money on hardware, which makes people happy, at least the company's happy. So I originally was going to title my talk on conditional branches in optimal decision trees, but I decided to name it in a more cheeky fashion, improving optimal decision trees, in that there are some optimal decision trees that aren't really optimal and that can be improved, and I'm going to show how to do this. As David said, my name is Michael Baer, and I do work for Electronics for Imaging. We're a company that makes enterprise print solutions, so very fast, very big, very expensive printers and devices that go into printers. But of course, this is a problem that is a little more universal than that. So again, a simple example is a case switch statement. How is that going to be implemented in practice? Well, in practice, you might just want to divide and conquer. If you assume everything has the same probability, then you will want to have the solution space and halve it again until you get what you want. So that's good. And if I express that in terms of a decision tree, and time is, of course, vertical in this particular problem, then everything happens at the same time, assuming that every instruction takes about the same amount of time. But the fact is that in real computers, every instruction does not take the same amount of time. And what I want may be this, but what I get may look a little more like that. In this particular case, that's not too big a difference, but in more complex problems, I might want a tree that looks like this, and so it's pretty balanced. It's good for binomial distribution because the center occurrences are the most likely. But if I don't keep in mind how my hardware looks, in terms of time, what I might get is a tree that looks like this. Now, why is that the case? Why aren't branches fixed time? Well, simple solution, simple explanation is pipelining solves. And I'm going to have to talk about computer architecture a bit. Maybe I should ask you how many people already know about this. So I see about 2/3. So for the 1/3 that remains, I'm going to explain it. Hopefully, the rest of you can follow along and humor me. So in modern machines, tens of instructions, or maybe scores of instructions, take place simultaneously, from the time that the instruction is originally fetched from the code to the time it's retired, to the time that it's done everything that it needs to do. So that works well for most instructions, but one question is, well, in the case of branches, what actually happens? So here time is along the horizontal axis, and I have a series of instructions that take place one after another. Some instructions take place at the same time. Some instructions you have to wait for part of the previous instruction to be over before you can start, for one reason or another. But the instruction that I'm most worried about here is the orange instruction, the branch instruction. In the branch instruction, I'm only going to know what the outcome of the branch is here, what the outcome of the comparison is that predicates my branch. So if I only know what my next instruction is going to be here, then that's trouble, because if I were to do this in the most straightforward manner possible, I'd just wait for the outcome and then start a new instruction. So I'd be basically costing myself lots of cycles, maybe 15, 20 cycles, which might correspond from between 15 and maybe 50 instructions. That would be very bad. And so because I don't want, especially in a decision tree where you're going to have branches occur over and over again. So what would be better is if I could somehow divine my solution ahead of time. And the way this is done is basically a guess. It's called speculative execution, but of course that's just a fancy name of saying guessing. And if I'm going to guess and not wait for the instructions to actually calculate what my outcome is, then of course sometimes I'm going to be wrong. And when I'm wrong, I'm just as slow as when I waited, because I'm going to have to wait, execute a bunch of instructions, and then realize that I shouldn't have executed all those instructions, and I need to go back to the state that my microprocessor was in beforehand. But if my prediction rate is about half, or even 3/4, or in the case of some applications, maybe 95%, then on average, I'm going to be much, much faster, because I can just say, well, I'm going to assume that I just, for example, fetch the next instruction. And if I fetch the next instruction, and that instruction turns out to be the one that I should have fetched, then that takes barely any time at all. So, but because a correct guess is much quicker to execute than an incorrect guess, that results in an asymmetry, in that if I'm going to have a branch, then for one particular case, my branch is going to take maybe 2 cycles, and for another case, it might take, say, 11 cycles. So if I ignore that in coding my decision tree, if I assume that every instruction takes the same amount of time, I'm going to wind up with that asymmetric outcome that I had in one of the previous slides. A much better way of approaching this is by saying, well, I know I have an asymmetry. Let me just fix that asymmetry and come up with an optimal tree based on that fixed asymmetry. And that's nice. It can result in good trees, but you can do that one better. And the way of doing it better is to control the asymmetry. Sometimes the asymmetry goes this way, and that might correspond to a greater than or equal to function. But if I change that, if I rearrange my code and change the greater than or equal to a less than, then I'll have an equivalent set of instructions that will have a different asymmetry. So let me just make sure. Is there anyone who's lost now? Because I want to make sure that you all are understanding this. OK, good. So the most simple type of prediction is static prediction. And static prediction happens on processors like that, which you'd find in an iPod or in a cell phone, which are all of the ARM family, actually. And similar type of processors also have static prediction. In a static prediction, you follow a simple rule. And usually the rule is as follows. If I'm going to branch to something that's ahead in terms of the code space, then I'm assuming that that branch isn't going to be taken, because that might just be a special condition. If I branch back, then I'll assume that the branch is taken because it's a loop. Now in this problem, I'm going to assume that all branches are branches ahead, and so I can just assume that the branch is going to be assumed untaken and code accordingly. So the inputs to this problem are the probability of each outcome event, each outcome interval, and the time cost asymmetry that the processor presents to me. And as an output, I want the decision tree. And the decision tree can be expressed in terms of the splitting points, which is the number that I say, is this greater than or equal to that number, or is that less than that number? So if my inputs are 1 through n, then that's going to be 2 through n, because 1 is trivial, because everything is greater than or equal to 1. All the inputs are. And I'm going to have a bias, the asymmetry, which I have to physically code into my assembly language or whatever language that I have. And formally speaking, that can be put as follows. Of course, formal formulations are necessary, but not always that interesting. The input, again, is the probabilities and the asymmetry, and the output is the binary tree with an assignment of the asymmetries, which are represented by B. And that should minimize the expected number of time that it takes to actually get this done. So before I look at solving this problem, I want to bring up some problems that are related to this problem. Some problems that are also decision tree problems, but take a slightly different tack. So one of these problems is sometimes called the cart problem. And what that problem is, instead of saying, is this less than, or is this greater than or equal to, I say, is this in a given set, or is it not in this given set? So this is a very generalized form of this problem that is applicable to certain problems. It's actually one of the ways of thinking about it, and I won't fully explain this, is Morse code actually operates like this, because you can assign any code word to any given any given letter, and in order to optimally assign them given a certain probability, you would solve this using the CART problem. And because it's a relaxed version of this problem, if you solve this problem, the solution to this problem will be slightly quicker or around this, or exactly the same time as the problem that I'm considering now. So it's a good lower bound for performance. A good upper bound for performance is the case 1 that I talked about, if you assume that the asymmetry is fixed. And that is what I'll call the Itai problem after the person who looked into that particular problem. And other problems are related to this current static prediction problem according to this grid. If the costs are the same, then the static problem becomes what's called the Hu-Tucker problem, and the CART problem becomes the Huffman problem. Now, I mentioned Huffman coding before. It's the same problem, but before I was talking about, well, this is a good way to implement Huffman coding. Now I'm talking about the actual Huffman problem and finding of the optimal solution. So this is related in Huffman coding. This is related with Huffman coding? Related with Huffman coding in 2 different ways. And that's why I'm interested in it, because that's what my doctoral thesis was on. But this is actually applicable to a wide variety of problems. So I already said before that I want to minimize the expected cost, the expected time in cycles. And that is equal to the weighted by the probability of each outcome, how long it takes to get to each outcome, which is determined by what type of asymmetry I have, which is B, and the amount of time each asymmetry takes and how many steps I have to get on the way to the solution. So as I said before, if I relax the problem, I can come up with a lower bound for the performance of the problem. If I constrain the problem, I can come up with an upper bound. So these lower and upper bounds can actually be easily computed, far more easily computed than actually solving the problem at hand. And they've been looked at in other papers, and these are what they are. They're relatively close to one another. Of course, it depends on your various values. So if I say, well, I'm not sure if I really want to use a decision tree, I have this other method which is which may be better or may be worse. You can figure out whether it's better or worse than this range in which this value, which you'll have to calculate, lies. So everyone's with me with that as well, correct? Okay. So I've built you all up, and it turns out that the algorithm for solving this is extremely straightforward. This is not exactly a stroke of genius to come up with the idea that it's a dynamic programming algorithm that takes advantage of the fact that after you make the first decision, all decisions after that have to be optimally made. And you can show via an exchange argument that you can build the problem up as a dynamic programming problem that goes with the size of the subtree and builds it up until you get the size of the subtree that you need. And so this is the formulation of it. As with many mathematical formulations, it looks a lot worse than it actually is. So I'm going to go through an example to illustrate how it really works. And the example has input as follows, with probability 0.3, 0.2, 0.2, and 0.3, with an asymmetry of 3 versus 1. I want to come up with the optimal decision tree for that. So you start out, if you start out knowing that your solution is 1, then of course your cost is going to be 0. So if you know so for these singleton cases, you have a 0 cost, and this is the number for the item that you have. But over here, the item, S, the last thing here, corresponds to the splitting point. So if I have items 1 and 2, I'm going to try to figure out whether the item is greater than or equal to 2. If it is, then it's 2. If not, then it's 1. So these are really straightforward in terms of how to calculate the total probabilities and the splitting point. And also relatively straightforward is the cost, because I'm going to say, well, for the least likely item, 2, I'm going to have that take 3 cycles, whereas the more likely item, 0.3, is going to take 1 cycle. So 0.3 plus 0.2 times 2, or times 3 actually, because of this, is 0.9. And I continue to calculate that for each particular value. And then for these values, I have to figure out which of my two choices is best. So I go to my two possible choices for each of these and calculate similarly until at the end, I get what my optimal performance is, which is 3.6. I didn't tell you what units I'm using. Perhaps I'm using cycles. If it's 3 to 1, I'm probably using groups of 2 or 3 cycles. But the idea here is that you get the optimal solution, and you know the splitting point is here. And then from there, you can calculate all the other splitting points and note that your tree is going to look like this, an upside-down version of what you get by resplitting. So it's a relatively straightforward approach. And it takes O of n cubed time and O of n squared space, because you have to store this triangle, which is O of n squared space. And for each entry in the triangle, you have to calculate all O of n possible selections. So that's somewhat slow. If n gets large enough, it will be very slow. So can I come up with a faster way of doing this? Well, one way of solving similar problems, including Itai's problem, was known by Knuth. And I'll call it the quadrangle inequality. Knuth isn't actually the one who called it this, but he did note a certain property which meant that you could actually make this from O of n cubed time to O of n squared time. And if you can do that in this case, that would be great, but you can't. And the actual example that I used is a counterexample to this. And I won't go through this, but if you want to write down the numbers and try it yourself, you can see that that Knuth's approach doesn't actually work. An even better approach would be a Huffman-like approach, because that would be O of n log n. And this was found by Hu and Tucker. And actually, Knuth is the one who showed that it was O of n log n time. But again, there's a counterexample to this. So not quite sure how I can get better performance than this, but it doesn't really matter that much, because n is going to be relatively small. If it were large, then I would probably want to use a jump table or a lookup table or some other method other than a decision tree. So for small decision trees, O of n cubed isn't too much of a deterrent for me. So another example is if you have a binomial distribution that has this asymmetry, then this is the optimal tree, and the number of cycles that it takes to get to a decision on average is 12.98. If I were to assume a fixed asymmetry, then I could only do as well as 15.1, which is 14% worse. So obviously, much better to do it according to this formulation. A more complex example is in terms of Huffman coding. If you have a bunch of words that are distributed according to Zipf's law, as words often are, and you want to come up with a Huffman table for it, you'll have the following probabilities that the lengths of each of the code words are these particular numbers. And if you want to code for this, have a decision tree to see how long each code word is, then the decision tree will look like this. And if I were to solve this in the most straightforward fashion, then I wouldn't get this tree. I'd get a slightly different tree that's actually 3.1% worse. So this speeds up Huffman coding by this particular step of Huffman coding by 3.1%, which is nice. So that's good for iPods. But for Pentiums, things are a little more complex. And depending on how my time is, I don't know how deeply I'll get into this.
Got another 15 minutes or so.
Got another 15 minutes. So hopefully you can indulge me and I'll get into it. Processors such as the Pentium 4 use dynamic branch prediction, which means that they have a slightly more complex way of predicting whether branches are taken or untaken. What they'll do is they'll use the results of previous branches to calculate that, which makes things much more complex. But for most applications, it makes things anywhere from a little bit faster to a lot faster. So that's kind of nice. But in this particular problem, it doesn't do this. It actually makes things slower. And the reason is, if you know which branches are going to be more likely taken and which are going to be less likely taken, then of course you'll always want to assume that you take the more likely route. And you don't need any dynamic modeling. And even though the dynamic modeling can get rather complex, it turns out that in order to model this particular problem, because you're assuming that each decision tree is going to be independent from each other decision that you're going to make. If you make multiple decisions at a time, you assume that they're all independent. And because each particular step of the decision tree is fully determined by whatever steps precede it, then you can actually model this quite simply as a single Markov chain that you want to find the stationary distribution of. And in Intel architectures, that Markov chain is relatively simple. These T's and N's over the arrows represent that if a branch is taken, you move, and you're in this state, you move to this state. So if it's taken, 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 you're eventually stuck in this state, where you always assume this T in the circle, which is that every other branch will be taken. If you're right, you go back to this step. If you're wrong, then you go over here. So if a lot of branches are taken, you're going to assume that the next branch is taken. And if a lot of branches are untaken, you're going to assume that the next branch is also untaken. So it turns out to be a pretty good method for predicting branches. But as I said, in this case, it makes things a little worse. Instead of having the probability of the less likely outcome be equal to the probability of misprediction, it turns out that the probability of misprediction will be slightly greater than the probability of the less likely outcome. And you can do that through analysis of the Markov chain. And if you do this, you find that the main two methods, A3 and A2 which is used by the Pentium, not actually the Pentium itself, the Pentium 2, Pentium 3, Pentium 4, Pentium Pro, the Pentium was actually a little broken. So if you were to try to optimize for a Pentium, you would actually do something slightly different than this. But they eventually fixed it. And so this is what you do for a modern Pentium. And other processors, maybe MIPS, because this is in Hennessy and Patterson's book, so one would think that the MIPS processor would use this technique. The curves differ, but it gives you a function for how long things are going to be expected to take. And taking advantage of this, you can come up with a general formulation. Instead of one of two possibilities, there might be one of k possibilities. In dynamic branching itself, there are only going to be one of two possibilities. But there are other things that you might want to do, such as conditional instructions or other types of models that are more complex. And in order to get all these complex models, I want to come up with a very general dynamic programming approach. And in that dynamic programming approach, you basically say, well, what is the cost given that the probability of one-way branch is p prime, the probability of another way branch is p double prime, and I'm considering the tree between I and j, inclusive with I, with splitting point s, using method k. So I'm going to have k possible methods. You can have one asymmetry, another asymmetry, a different method. Combine it all, and you get a general formulation like this. And that's going to take O of m to the n cubed time, where m is the number of possible k's, the possible splitting methods, which if k is small enough is basically O of n squared, just as in the previous approach. So what I've done here is to use the actual behavior of conditional branches to impact decision tree design to make sure that my decision tree truly takes the least amount of expected time. And in some sense, this results in better than optimal trees, because like I showed before, if you use previous methods to find optimal trees, they won't truly be optimal in terms of taking the least amount of expected time. And unfortunately, I've shown that the most straightforward, fast methods of finding decision trees don't apply here. But because n is usually pretty small, slow methods are efficient enough for most purposes. So finally, I want to end by saying this is what I've done. What I haven't really done is go into enough real-world applications. And that's one of the reasons I'm here, is I wanted to ask if any of you had any real-world applications. If you want to, you can come see me after the talk or come talk to me, because I think that this is kind of something interesting to look at, but it's even more interesting if I can show, here's a problem that I had, I used this technique, and suddenly my solution is a lot better than it would have otherwise been. But for those of you who don't have problems like this, this concludes my talk.
Binary branches, were branches either going to be taken or not. Have you looked at comparing these kinds of tables with just using a jump table? Just a compute branch?
Well, yeah, I'll repeat the question. The question was, how would this compare with a jump table? Can you analyze a jump table in a similar fashion? And what I sort of pointed out was that in the case of a jump table, you would have to analyze that in a different way, see how fast the jump table was, and then either solve this problem or use the entropy bounds that I showed before to come up with an estimation of how long the non-jump table approach is going to take. And if the jump table approach is faster, you use a jump table. If this approach is faster, then you don't. In some cases, a jump table isn't really applicable because if you've got, say, the estimation of a division, then you really have to either do the division and use the quotient to figure out what interval you're in, or you have to use a method like this. So, I did emphasize cases, statements, and ifs and thens, but of course, you can do things that are slightly more complex.
So the C's, the cost function, basically,
Mm-hmm.
you kind of assume it's constant. So I would just believe if you reorganize your branches, that function changes.
Okay, so. So you were saying that I'm sort of assuming that my costs are constant. And it is true that in the more complex processors, they won't be. And that's why I had that final C of k function, where each k is to determine, well, if I guess I shouldn't have stopped this. Let me go to the slide so I can show you what I mean.
And even in that case, how do you know these costs? Basically, you have to speculate.
Well, I mean, presumably you know the behavior of your processor. You're saying, well, how do I know the costs? I have to speculate. And in some cases, that may be true. If I don't know the behavior of my processor, which in many cases, perhaps, say, AMD or Intel didn't tell me, and the processor is too new that someone else didn't reverse engineer it and figure out how well it performs, then yeah, these numbers might be a little hard to come by. But when I can come by these numbers, then I can take into account not only the probabilities involved, but also the positions. For example, one thing that you might say for the division problem is, well, it's a lot easier to shift a number than it is to multiply it. It takes a lot less time. So if my I, j, and s are such that I can do the comparison with just a shift instead of a multiply, then my cost is going to be much lower.
In this case, it's easy, but if you have like a nested switch statement and you have no clue how fast each branch executes, what do you do?
I'm not sure what you're asking. Could you say that again?
In the case of the division, that's easy, right? Because you know that a simple comparison is much faster than the emulation of the difference function. But in a more general case, how do you get to those weights or to the cost function? I don't really see it.
Are you saying that I don't know what my probabilities are, or that I don't know what my cost functions are?
In particular, it depends when you have no clue about the costs. That's what I'm saying.
Yeah, I mean, if you want to optimize this for a family of processors, for example, then it's a little harder, especially, or if you want to optimize this for a particular processor that you don't know the performance of, then that can be problematic. And yes, I am making the assumption that I know my processor well enough that I can actually do something like this, which might be an improper assumption in some cases. But in most cases, you have some idea based on reverse engineered versions of previous versions of the processor what performance is like. And you might not actually get the optimal performance, but you might get a better performance than if you didn't take that into account at all.
So you mentioned smaller problems, right? Because if you have this endless if then else, decision tree, that at one point it will be smaller than any lookup table. Right? It will be slower than any lookup table. So it will only work for smaller problems.
Yeah, you just repeated the point that this is best for smaller problems. If the problem's big enough, then you should use a lookup table. In some instances, you can't quite use a lookup table, but you use something equivalent like a division, like a hardware division or an emulated division, and that's actually going to be faster than the method that I've proposed up here. And of course, I don't deny that, and I say it explicitly. And one example of that is that in this Huffman problem, this is based on a paper of fast Huffman coding that was put out about 9 years ago. And in that paper, they compared using a lookup table with using a decision tree that looks almost exactly like the decision trees that I show up here. And I contacted the author, and he said, well, I formulated that decision tree using the Hu-Tucker algorithm, which means it won't be as fast as it needs to be. And in some cases, the decision tree was faster than the lookup table. In other cases, the lookup table was faster than the decision tree. So obviously, you want to solve the problem according to the way that you want to do it optimally. And another thing that I didn't mention is that if n is large enough, then you have to worry about problems like code caching. And if that starts to be a problem, then in some cases, all bets are off because this model just doesn't conform to that. Any other questions?
Well, thank you, Michael. And thank you all for coming.
Yes, thank you.